Okay, try to imagine a number so ridiculously big that it would take you page after page after page just to write it down. A number that makes something like the distance to the nearest star look like pocket change. Today, we're going to get into Merg-E, a programming language built from the ground up to handle and, more importantly, protect numbers on that kind of mind-boggling scale. So let's just get right to it. The first question that pops into anyone's head is, why? I mean, seriously, why on earth would you need an integer that's 16,384 bits long? A regular 64-bit integer can already represent a number bigger than all the grains of sand on the planet. So what kind of problem needs a number that astronomically huge? Well, the answer gets right to the core of our digital security. And there's your answer. Merg-E isn't a general-purpose language. It's what we call a domain-specific language, or DSL. It's built for a very specific job. The new world of the decentralized internet, Web 3.0. In that world, security is absolutely everything. Think about it. The encryption that protects your bank account, your private messages, all of that relies on cryptographic keys that are really just unimaginably large numbers. Merg-E is designed to make working with these numbers not just possible, but fundamentally safe. But, and this is a big but, there is a huge problem. You can have the most precise, gigantic number in your program, but the moment you try to send it to another system using JSON, which is pretty much the standard for web data, it all falls apart. The number gets corrupted, rounded off, it becomes an approximation. And that's not just a little bug, it's a catastrophic failure that can completely break security systems. So Merg-E really has two big challenges to solve: how to manage these numbers inside the language, and how to get them out into the world without losing a single bit of data. So to tackle this whole massive number problem, Merg-E starts right at the foundation with its integer system. And this isn't just about making bigger buckets to hold numbers. It's about building a digital fortress, one bit at a time. Let's just take a second to really appreciate this number. 16,384 bits. To put that into perspective for you, if you wanted to give every single atom in the known universe its own unique ID number, you could do that, and you'd still have an almost infinite amount of room left over. This isn't just overkill. It's about future-proofing cryptography for years, maybe even decades to come. And Merg-E doesn't just hand you one giant integer type and call it a day. No, it gives you an entire toolkit. You can see here you get everything from a tiny uint1, which is really just a different way of saying true or false, all the way up to those 16,384-bit monsters. This lets developers pick the exact right tool for the job, which means you get both maximum security and fantastic efficiency. Okay, so we've got these colossal numbers. That's awesome, but what good are they if you can't even do simple math, like adding two of them together without the whole program crashing? This brings us to Merg-E's second really brilliant idea, a system that guarantees every single calculation is not just accurate, but totally safe. You know, this is one of the oldest bugs in the book for programmers. It's called an integer overflow. Think of an old car's odometer. When it hits its max mileage, what does it do? It just rolls right back over to zero. That's an overflow. In software, that kind of silent error can be absolutely disastrous. So how does Merg-E make sure this never happens? Let's walk through it. Say you're multiplying two 4-bit numbers. The biggest value a 4-bit number can hold is 15. Well, 15 times 15 is 225. And to store 225, you actually need 8 bits of space. Most languages would just give up and give you a completely wrong answer. But Merg-E's compiler is smart. It sees this coming. It automatically, behind the scenes, creates a temporary 8-bit space to do the math in, just to make sure the result is perfect. And this clever little trick has a name. It's called a virtual type. You can think of it like a temporary scratch pad that the compiler pulls out to do its work. It doesn't actually exist in the final code. It's like a helpful ghost that appears just long enough to ensure every single calculation is flawless before the program is even built. But it gets even better. Merg-E doesn't just keep this power for itself. It actually hands this overflow predicting superpower over to the developers so they can write their own custom functions that are just as safe and flexible. And they do this through a feature called integer bitlength generics. This is where things get really cool. Now, I know what you're thinking. This looks like absolute gibberish, but what you're seeing is actually some brilliant engineering. In programming, generics let you write flexible code that works with different types of data. Merg-E takes that idea and just pushes it to the next level. Those symbols, the eyeball and eyeball inflammation eyeball, are special operators that do math, but not on the numbers themselves. They do math on the size of the numbers. It's like giving the compiler a blueprint to build the perfect, custom-sized box for the result every single time. It is type safety on a whole other plane. So let's recap. We can create these giant numbers. We can do math with them with guaranteed safety. But what happens when we need to send them out into the world, when we have to cross that dangerous bridge called JSON? Well, that's where Merg-E's third and final core innovation comes into play, high-fidelity JSON. This slide really says it all, doesn't it? On the left, that's what happens when you try to put a big number into standard JSON. It gets mangled, rounded off, and becomes totally useless. But look at the right. Merg-E's high-fidelity JSON, or HFJSON, has a clever solution. It just wraps the number in a special descriptive string, preserving every last digit with perfect accuracy. So how does this actually work? Let's break it down. You can see it starts with a little HF tag. That's a signal to any program that this isn't just a regular string. Then, it describes everything about the number, its type, its exact size in bits, and even the base it's written in. Then you have the value itself, and after that, a checksum. A checksum is basically a unique digital fingerprint that proves the data hasn't been tampered with or corrupted. It's a completely self-contained, high-precision, tamper-proof package. All right, so we've looked at the three core pieces of the puzzle: massive integers for raw cryptographic power, safe math to prevent any and all errors, and high-fidelity serialization to talk to the rest of the world. Now, let's just step back and see why this whole system working together is such a game changer. So let's quickly recap what we've covered. First, Merg-E gives you the horsepower you need for serious cryptography with its huge native integers. Second, it acts as your safety net, completely eliminating overflow errors before your code is even finished, thanks to virtual types. And third, it builds that secure, lossless bridge to the outside world with high-fidelity JSON. You really can't have one without the others. Each part is crucial. When you put all of these features together, what you get is more than just a programming language. You get a fortress. It's an environment that was designed from day one with the goal of protecting your most critical data. And in the world of Web 3.0, decentralized finance, and high-stakes applications where a single rounding error could cost millions, this kind of deep, built-in security isn't just a nice-to-have. It's an absolute must. Merg-E really shows us a different way to think about programming, a way where safety and precision aren't just an afterthought you try to bolt on later, but are baked into the very DNA of the language. As our world gets more digital, more decentralized, and frankly, more dangerous, it really makes you think, is this the future? Are we going to see a new wave of languages that aren't just powerful, but also fundamentally wise? It's definitely a question we're thinking about.